Okay. So in this lecture, we're going to we've actually kind of already done this before, but hammer it home even more how we use these electron pushing arrows in reaction mechanisms. Okay. We sort of have already been doing this. We introduced it first with resonance. We even talked about it a little bit more and how it extends to reactions. So we're just going to build on that even more. This is a hugely important concept for the course of general chemistry. These electron pushing arrows are going to be how we talk about chemical reactions, how we understand them. So making sure that we know how to do that is really important. When we're talking about non-radical reactions, or again, these ionic reactions, the electron pushing arrows that we see are going to fall into these 5 categories. All right, so that's a lot of what today this lecture is going to be about, is identifying which of these categories that it belongs to. You can have a nucleophile attacking an electrophile. The loss of a leaving group, so we'll see what this means here in a second. One of the ones that we've already seen are acid-base type reactions or proton transfers. Rearrangements is actually something that's going to be saved for the carbocation lecture. So we won't cover that in this one, but that will be one that we cover in the carbocation section. And then another one that we've already seen is how these pushing works with regard to resonance structures. Okay, so these are these categories that we want to try to understand our reactions through. Okay, so first of all, nucleophilic attack. You guys are experts now in identifying nucleophiles and electrophiles. So which one of these is my nucleophile and which one of these is my electrophile? My electron-rich bromide ion is my nucleophile, and the carbocation is an electrophile, right? So nucleophilic attack is kind of exactly what you would expect by the name, which is your nucleophile with its pair of electrons coming and attacking the electrophile, right? The nucleophile has electrons to give, the electrophile really wants electrons. So the tail of that arrow starts on those electrons, on that nucleophile, and the head of the arrow ends at the electrophile. And this is going to be bond formation that's occurring here. Okay, so this is nucleophilic attack, right? When you have your electron-rich species attacking that electron-poor species. I just want to sort of point out, and I'll go through a few examples here, but let's say that we didn't have this line here. I just had my products and my reactants. How am I going to go about solving this? Well, what I'm going to do is look and see what bonds have been broken or formed, right? So I'm looking on the left, I'm looking on the right, and I can tell that this isn't on my reactants. So that has to be the bond that's being formed. That's how I know that there's an arrow pushing arrow that grabs an electron from the bromide and attacks that carbocation. A little bit more complicated of an example of a nucleophilic attack. This one occurs in 2 steps, okay? And before we even get to the product, looking at the products, let's see why that is. Well, I have my nucleophile, in this case water, attacking my electrophile, what site on here is the electrophilic site? Electrophilic, carbonyl carbon is something you're going to hear me say a billion times. But yes, is going to go and attack that we have your nucleophile attacking that electrophilic carbonyl carbon. But I can't stop there, right? What's wrong with this carbonyl carbon now is that it has too many electrons. So concurrently, what's going to happen is a pair of electrons going to jump up there, right, onto that oxygen. So that's how I get my product. Notice how charges are being kept track of. You have a neutral species, a neutral nucleophile attacking an electrophile. That means it's going to end up having a positive charge. It's lent its pair of electrons. Likewise, when this pair of electrons jumps up here, you get a negative charge on that oxygen. And again, if I'm going to try to like do this where I'm just looking at the products, I'm going to identify that this bond right here was the one that was formed, And this pair of electrons right here that was in that pi bond, that's what's been broken, right? So I need to have one arrow indicating by bond formation and one arrow indicating, so this is formation and this is breaking. Again, this is just nucleophilic attack, but there's more than one arrow so that we can not do anything illegal in terms of breaking carbon's octet rule. This second arrow here can be thought of as a resonance arrow. Remember, we showed how we have resonance in these carbonyl bonds because of the difference in electronegativity. All right, loss of a leaving group. So again, kind of what it sounds like. This is when you have a group, in this case it's going to be bromine, that leaves, all right? This is going to be then bond breaking that you're going to be showing with your electron pushing arrows. The halogens are classic leaving groups, okay? That's because good leaving groups are bad bases. Likewise, strong bases are bad leaving groups. So bromide ion is a terrible base, and so that's what makes it a good leaving group. Let me just actually modify this example a tiny bit. Let's just say we had an alcohol here. And I wanted that group to leave. What would my leaving group be? Well, that would be a hydroxide ion, which is a pretty friggin' good base. So alcohol groups are not good leaving groups. What we do when we want to have a reaction where we get rid of an alcohol group is we carry it out under acidic conditions so that that alcohol group gets protonated. And then that becomes a really good leaving group, because what's my leaving group now? I have water. This is my leaving. Likewise, this is my leaving. I have water as my leaving group, and that's a great leaving group, okay? Because water is not a very good base. So I'd be left with a carbocation and a water as my leaving group in that reaction. So that's another category of these electron pushing arrows that you're going to see. First was nucleophilic attack, also the loss of a leaving group. And again, you can sort of see that in, it doesn't always have to be just one step. It can be paired up with resonance type arrows like here. So everybody take a second and make sure that you can draw the product of this reaction. All right, so this pair of electrons comes down. Pair of electrons that was in this bond breaks. Let's just follow these things here. So this pair of electrons is what becomes this. Now I have this pair of electrons. At the same time, this one came down here. That one didn't move, actually. That pair of electrons is that. And now I have kicked off my chloride leaving group, right? So in terms of labeling this structure here, these were resonance type arrows, resonance type, and here was my leaving group leaving, my chloride ion being kicked off. Okay, oh, let me put my charge in, not be sloppy. Cool. Okay, another thing, just to take a step back, just like we did, what we talked about with resonance, is conservation of charges should also always be a thing, right? So here I had a negative, a positive, and a negative, so I have a net charge of -1. I should have the same thing over here, all species considered, and so that is the case. But just keeping track of charges is super easy to mess up on, and so when you're done, take a step back, add everything up, and make sure you have conservation of charges. All right, proton transfer. So y'all are experts at this because proton transfer is just a fancy word for acid-base type reactions, right? We say that something is protonated if it accepts a proton. So here we have, this is an example of a carbonyl oxygen acting as a nucleophile. It's going to go and grab that hydrogen and become protonated. So this would be an acid base. You could say that your hydrogen, your acidic hydrogen, is playing the role of an electrophile. We're going to kind of keep this idea of electrophiles and acidic hydrogens a little bit separate. It's kind of just a semantical thing, but just FYI, like on your homework. Whenever I'm asking for electrophiles, I'm not talking about acidic hydrogens. Acidic hydrogens, we all know, will accept electrons. And then the reverse would be a deprotonation, right? This would also be this acid base or proton transfer type reaction arrows that you can draw. So in this case, you would have a proton leaving. Really what we would see in our reactions is we're going to see a base that accepts. Sometimes it's just this generic B base that works. If we have a catalyst, an acid catalyst, I like to reform my catalyst. But yeah, bottom line is something's going to be accepting that proton that's just floating around in solution. Just another example of electron or proton transfer, but then one that's followed by a sort of resonance type as well, would be this accepting of this hydrogen from base. Pair of electrons goes down to form a double bond, so this would form this type of structure here, right? But these are all just examples of proton transfer arrows. You know, arrow pushing that represents proton transfers. Either a deprotonation or a protonation. All right, so now let's look at this big, ugly reaction mechanism. This is a what, 1, 2, 3, 4-step reaction mechanism here. And we're gonna go through and follow all of our arrows, and then we're gonna classify them as being part of one of those 3 groups. All right, so again, how I'm gonna do this, how I would do this if this was my homework problem or whatever, right? This is a diagram where all of the arrows are missing. So I gotta be able to put those in correctly. Well, I'm gonna look from, from reactant to product and see what's being formed and what's being broken. In this case, the only difference is I have this new oxygen-hydrogen bond here. So that's gonna be a bond that's being formed. But the bromine's not going to come along with it, so that means that bromine's going to accept that pair of electrons. Okay, so classifying this, which of those 3 categories is this a nucleophilic attack, loss of a leaving group, or proton transfer? This would be a proton transfer. All right. All right, now next step. It tells me that water's leaving. That's what this minus H2O means. Even if that wasn't there, you could just look at your structure here and realize that a bond had to have been broken, and that's this bond here, this oxygen-carbon bond. So which category would this be? This would be loss of a leaving group. Okay, again, notice how it's that protonated alcohol group that we said was a really good leaving group. We're going to see that over and over again. Now we're left with a carbocation. And what the heck is going on here? We have this, let's see, 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6. So all my carbons are accounted for. There's no, nothing that's been lost. But of course, these structures look very different. So what has occurred here is that my positive charge has migrated over here, and a methyl group has migrated over here, kind of switched places. This is going to be one of these rearrangements that we're going to see, we're going to focus on in the carbocation lecture. There's something that's specific to carbocations. But what really is going to happen is this bond that's from this methyl group, these electrons that are in this carbon-carbon bond are going to switch. And now I have my carbocation over there. So just to keep track of what's switching here, this guy jumped from over there and is now over there. Okay. Gave its pair of electrons to that carbon, which moved that positive charge. We're going to see that has to do with the stability of this carbocation compared to this guy. This guy's more stable. But let's not harp on that too much now. This is a rearrangement. Okay. And now looking at this last step here, I notice that I have the formation of a new bond on my product side, which means that I need to represent that with my electron pushing arrows as a nucleophilic attack. All right, so notice how in this big, ugly reaction mechanism here, I was able to go through and put those arrows into these categories. It's just a good check to make sure that you're not doing anything crazy and wild. You know, sometimes in organic chemistry, people start to panic and they just start drawing lines everywhere and breaking bonds and everything. Everything should fit this pattern that we've learned about thus far. Let's just go over a few rules. We've sort of already done this, but just to beat a dead horse here, make sure that we all got our rules for our arrow pushing here, electron pushing. What's the base of your arrow? Base of the arrow has to be on a pair of electrons, whether that's in a bond or a lone pair. Base of electron is always on a pair of electrons. Okay, so here's an example here. When it's on a lone pair and reaches over, this would be formation. When it's on the bond and jumps up, that would be breaking. Okay. Yeah, so just make sure the base of that arrow is on a pair of electrons. What about the tip of the arrow? The tip of the arrow should be on an atom, right? And that's either going to be on, when you go from a bond to the atom, that's the formation of a lone pair. So it goes from a bond to a nuclei. When it's between nuclei, so on a lone pair on this atom over to this atom, that's going to be bond formation. Okay. In this case, what would be my products that are formed? Bond formation. So now I got a new bond here and then my broken bond here. What would we, if we wanted to be really good, what would we call this step here? This is the loss of leaving group. And what about this one here? I think I'm jumping the gun. I think I said this on another slide. Anyways, this is nucleophilic attack. Right? So again, we can categorize our electron pushing into those categories that we learned about at the beginning of this lecture. The last, the last important rule for electron pushing is you're never going to exceed the octet of any electron, of any atom. So in this example here, one of these is correct and one of these is incorrect, right? Which one is incorrect? So that's going to be this one here on the left because it violates carbon's octet rule. So if you want to have, let's say that you realize that this is your nucleophile, this ethoxide ion here, and you have this carbon that you want as your electrophile, and you know you need a nucleophilic attack. That's great, but it has to be accompanied by the loss of a leaving group, for example here, so that you don't violate that octet rule. So that's going to be one of these principles that we know that this bond needs to form, but how do we do it in such a way that doesn't violate the octet rule? That's just a consideration that you're going to have to make in these reaction mechanisms. All right, and then the last one, which is what I said I kind of jumped the gun on, is you should be able to categorize your arrows, right? To make sure you're not doing anything crazy, you should always be able to sort of fit it into one of those nice, neat categories that we talked about at the beginning. Again, this example shows a nucleophilic attack followed by loss of a leaving group, right? So those all fit. Why would the arrow below be unreasonable? Well, because you're breaking carbon's octet. It also wouldn't fit into any of those categories. I mean, we did talk about how double bonds are nucleophilic, but this is not an electrophile, right? So you could tell that you're going to do something, you're doing something incorrect by making sure that, one, you follow those rules, and two, you can sort of see those arrows as falling into one of those categories. Okay.